All right. So it's my great pleasure to introduce this week's colloquium speaker, Kang-Kuen Ni. So Kang-Kuen is a professor of chemistry, chemical biology, and physics, and also a member of the Center for Ultracold Atoms at Harvard. So Kang-Kuen's group pursues, among other things, new approaches to create and gain quantum control over ultracold molecules for studies of chemical reactions, quantum information processing, and quantum many-body physics. Some recent achievements of hers include building single molecules using optical tweezers, studying collisions in a new paradigm where exactly known numbers of atoms are interacting, theoretical investigation of novel quantum computing schemes with molecules, and probing, steering, and controlling ultracold bimolecular chemical reactions from reactants through intermediates to products with quantum state resolution. So I'm really excited to hear about what Kang-Kuen is going to talk about today, partly because when she and I met some 11 years ago, she was doing a brief postdoc at Caltech, and we were working on something related but very different, where we were using optical tweezers to trap large mechanical objects, and we were hoping to use these objects for what at the time was sort of an idea for a field called quantum optomechanics. So after working at Caltech, she went back to atomic physics, and among other things has been using optical tweezers now to trap single atoms and bring them together to make molecules. It's really sort of audacious and beautiful physics, and so I very much look forward to this talk.
Thank you. Okay, can everyone hear me? Oh, is this on? It's good? Okay. Yeah, okay. Thank you, Del, for the kind introduction, and thank you for being here and for the invitation. It's a great pleasure for me to come here, beautiful place, and it's my first in-person colloquium since, a year and a half. Okay, so today I wanted to tell you about an experiment which I show in these graphs, where in my lab we gain quantum control of molecules. That's sort of the central thing of the technology that we're building. And in particular, we built these molecules from single atoms as shown here, and you can see that all the fonts are very small because this was originally designed for Zoom talks, and all these fonts are now too small when you're actually given in person, so time to change back, I guess. So starting from single atoms, we can pair them up, and these single atoms are trapped by these tightly focused laser beams, and we can pair them up to make a single molecule. So that's the story I wanted to tell you. So I find it actually difficult to breathe. Okay. So let me just jump into talking about optical tweezers. Optical tweezer was invented by R. Ashkin. We all know that light carries momentum and exert radiation forces, on objects, and a variety of experiments that us and you are working on are all sort of based on that fact that light carries momentum. Ashkin and others have been, thinking about observing light pressures on objects, and he figured out different ways of trapping objects, with different, usually using scattering, photon scattering, two different beams, or to levitate against gravity. And in 1983, he figured out he's able to, through using a high numerical aperture microscope objective focus beam to very tight spot, he's able to balance the scattering, the light scatter, the force of scatter light with the gradient force. So usually at these very tightly focused beams, very intense in the middle, and gradually the intensity drops, and there's a gradient force formed by that that focus profile, that one can have an equilibrium between the scattering force and the gradient force. And with a single beam, one can trap microspheres. And of course, that was a very important invention, and it led to huge sort of quantitative study in biophysics. For example, in the early 1990s, people can observe, for example, in this case, nanoscale motions of biomolecules, where one can attach these dielectric beads to, for example, kinesin motor. While it walks, they were able to make measurements of the discrete steps that these motor can walk, and also can measure minute forces in these samples. A very fun and a very fun movie that I've seen is this one, where these researchers in Netherlands, they can trap these microspheres in solutions in real time and play this real game, Tetris. And we can just be here and watch this game all day long. It's really, really cool. Really, really neat. Okay, so perhaps I will stop the playing this game here. Now, what I will be telling you about, instead of trapping the nanobeads in solutions, we're trapping single atoms. We're trapping single atoms in vacuum, and we can steer the atom just like that Tetris movies. That we can steer these beads, and we can steer the atoms to put together two atoms to forge a bond and make a molecules. In addition to using optical tweezers to build individual molecules, we also care about the quantum states of the resulting molecule. So before I go on to tell you the details of how we make these molecules, let me say a few words on the different molecular quantum degrees of freedom, which is important for the work that we pursue. So I work with molecule, and the goal is to have a lot of control over a molecule. And I think a molecule as perfect quantum machines. They have rich quantum degrees of freedom, electronic transition, vibration, rotation, and hyperfine, all different frequency, characteristic frequency that allow then as fingerprint transitions that allow us to probe them. In the usual chemistry domain, these degrees of freedom allow offering different imaging tools. For example, stimulated Raman imaging utilizing vibration transition or characteristic vibration transition can give molecular specificity under a microscope. So these are two of the same field of view image, but one with this stimulated Raman imaging, and you can see a lot more content about this versus the bright field image. And of course, that's very useful. Another example would be, say, the magnetic resonant imaging. Here is looking at where water is in this cup of corn, and that's utilizing the nuclear degrees of freedom. So, while these quantum degrees of freedom allow us to identify and study molecules in their innate environment, generating widely used tools in chemistry, biology, and medical setting, in the physics domain, these characteristic transition frequencies allow us to use them as standard for time and meters. The first atomic clock, 1949, was actually based on the vibration of ammonia molecules. And this was really because molecules easy to come by. You can get it in a bottle. And the technology, the microwave spectroscopy, microwave technology, was very advanced then, or at least very well developed, much more so than the optical, in the optical domain. So it was very easy, or relatively easy, to take molecule that has frequency that's in the technology band that's readily available at 24 gigahertz to use it as clock. The modern atomic clocks nowadays are based on no longer on these vibration of molecule, but rather on the the most advanced atomic clock is based on the vibration of an electronic density. So let me give you an intuition of how these intrinsic frequency in molecule or atom connects to a ticking of the clock. So what we're seeing here is our familiar S&P orbitals from your first year chemistry or physics course. When we make a superposition, drive a transition halfway, make a superposition of, say, S&P transition, we can see the ticking of the clock as these moving electron probability density. And of course, here I'm playing it 10 to the 15 times slower than how it's actually naturally ticking. But this same picture also apply to qubits and two-level system or other quantum systems. So you can think of a molecule with pair of states in for vibration, rotations, hyperfine, or electronic transition. They're all basically you can think of this same picture can map onto those different degrees of freedom. Now, atomic clocks has come a long way since its first development. Now, the best clock wouldn't lose 1 second in the whole entire age of the universe. And this is enabled by technology development of quantum control techniques, such as laser cooling and trapping of atoms, motivated really precisely by building better clocks. And we have come to a full cycle. Now the atoms has been tamed, we can apply technique to molecule. And more recently, we can cool and trap molecules. We can allow long interaction time between molecules and probe them for a long time. And a dream is to really build a more complex system from these building blocks, which are complex on their own and has a lot of knobs. People in this research field, ultracold molecules, pursue a wide range of directions from search of new physics, fundamental aspect of physics, to fundamental aspect of chemistry, as well as exploring sort of exotic quantum phase of matter and quantum information processing. So let me just go right in to say that our goal for a long time has to have been building single molecule. These molecules are in the gas phase. They're in vacuum. They're not in solutions. And we control all its quantum degrees of freedom in that we can make this molecule to be in the low vibrational ground state so that they possess a large dipole moment that we can manipulate them, and in the motional ground state. So every quantum state to be in the lowest one. There are actually currently two approaches for controlling neutral molecules, and I'm part of both approaches, where we can either from a laser cool ensemble of molecule directly grab single molecules, and these are image of single molecules fluorescence shown here, or we can start with single atoms and assemble the single molecule out of it, and this is the focus of today's talk. Okay, to start with single atoms, we had to begin by trapping two different species of atoms. We need to trap and manipulate them. So like the very first slide, I introduced optical tweezer. We basically focus, in this case, different color lights through microscope objective into our ultra high vacuum glass cell. And we can overlap it with our laser cool ensemble and grab a single atom out of it. So in our case, it was cesium. This was actually pioneering work in the early 2000s, where Philippe Grandier and others have shown that we can really get control over single atoms using these techniques. The process is stochastic, and I'll show you some data that we can really distinguish our signal from 0 or 1, between 0 and 1 atoms. So we follow these recipe, and we are immediately able to trap single cesium atoms for an ensemble of laser cool cesium atoms. when we tried to apply the same technique to sodium, we didn't immediately. Actually, took several months trying, making sure we're doing the right thing, and we couldn't see single sodium atoms. Well, it turns out that for sodium atom, the optical tweezer causing the light shift in a much more unfavorable way, where when we try to laser cool these atoms into the trap, these optical tweezer light shifted the transition far away to cause heating or inefficient cooling. So we pull out another tool from the atomic toolbox, atomic physics tools box, where we can alternate our tweezer light with our laser cooling light, our imaging or magneto-optical trap light at these kind of high frequency to make sure that that they never see each other, and therefore these light shift is eliminated and the atoms could be efficiently cooled down into the trap. And then with this implementation, we're able to get a single sodium atom for the first time. Now, with this setup, we're able to, we usually repeat our experiment many, many times. We can have a variety of different outcomes. We can have, most of the time, trapping a single sodium and single cesium atom side by side. Shown here, I'm just taking the image sequentially to have better eliminate background. So these are really, really side by side. And then sometimes just one species, either cesium or sodium, and some of the time where no atoms will be trapped. And this, of course, is not useful, but these single atom traps are still useful as a comparison experiment to distinguish between something that's a two-body process versus a one-body process. This is the kind of histogram we collect, and you can see that we can distinguish these two peaks well. On the one hand, we have, for a single species, 50% of time we don't trap an atom, and 50% of time we trap a single atom. Now, with two atoms trapped, these are image of the tweezer themselves. They're still far away, microns away, which is really too far in terms of making the molecules. So our next step is to bring them close together, basically overlapping the two tweezers so that the two atoms can be as close as possible. But to make a molecule is still very challenging for the following reason. So typically if we have a molecules, the two atoms in the molecule will have a sort of average spacing on the order of 0.1, 0.2 nanometer. But the best case scenario that we can pinpoint the location of an atom in an optical tweezer in this kind of the weakest direction, the wave function spread, the quantum mechanical limits of where the atoms will be, has a wave function spread of 50 nanometer. So taking the three-dimensional, this trap is three-dimension, that the wave function overlap of two atoms each have these kind of uncertainty in terms of its location. Their wave function overlap is on the order of 10 to the minus 6%. Okay. Furthermore, for atoms to collide to form a molecule, that binding energy needs to be released. And that binding energy in sort of temperature units will be 6,000 Kelvin. So if we start with very cold atoms, we want to end up with very cold molecules. That energy needs to be released. Okay. So that's, of course, a very challenging task. But luckily, there have been solutions, and this is actually something that I worked on as a PhD student. We had the solution to assemble molecules from atoms. The only difference here is what we've demonstrated prior, back in 2008, was from an ensemble as opposed to starting with single atoms. So the techniques are the following. We can do the first step to bind atoms into weakly bound molecules through a magnetic scattering resonance. Okay, so one can sweep a magnetic field near some resonance location to bring atom pair into a pair to be a weakly bound molecule, prepare them in a single quantum states, and then followed by the second step, where a two-photon coherent process shine light in a particular way to connecting these feshbach molecule state to low vibrational ground state can transfer the molecule into the state we want, and this stimulated photon takes away that excess binding energy and resulting in the molecule in the end not being heated at all. Okay, so just to sort of give you the punchline, so with these techniques, we demonstrated that from exactly 2 atoms, we can make a molecule with 30% efficiency. And this is, of course, much higher than that 10 to the minus 6 number that we would start out with if it just occurred by chance. Okay. So the exact steps that we do is to start preparing the atoms, so loading them, cooling them into their confining potential ground state. Okay, so these are cooling technique, which I'm not going to elaborate. It's also a well-known technique in the atomic physics, with one of the atomic physics toolbox, where we can cool them down to these harmonic oscillator level ground state. In particular, the spectroscopy shows that we can always bring the population to get one motional excitation. So these will be the data shown over here on the negative side. Well, on the right-hand side, depends on if we had cool it or not cool it, then you can see that once we cool it, then these sidebands, these peaks are gone, because once we prepare them in the motional ground state, we couldn't remove more motional quanta. So a ratio between these sideband height will tell us how much population we're able to bring it down to the motional ground state of the individual atom. So we can do a pretty good job. Now, these 2 atoms are prepared in their motional ground state, but in order to in order to make a molecule, they still need to be as close as possible. So we come up with sort of a carefully tuned, it's relatively straightforward, but still carefully tuned sequence in sort of a few millisecond time scale to bring the atoms from 2 different traps, 2 different locations into overlap, and then release one trap so that both of them end up in the same locations. Okay, each with this 0-point motion spread. So basically, that process preserved that these atoms still stay in the motional ground state. Okay, so with 2 atoms now in the trap, they can collide. Turns out there would be no reaction, meaning there's no molecule that could be made, because the binding energy needs to be extracted, and without a third particle being around, that's very difficult to do. So in order to make a molecule, we need to add the additional field, which will be the magnetic field and the light field, to extract that binding energy. So just through collision, they could collide, but they will not make a molecule. Okay, so from there on, we are, again, I apologize that these fonts are all too small. That starting with atoms, we can rent the magnetic field across and avoid the crossing to these scattering resonance to make molecules. And this is what our experiment, a small part of our experiment looked like, the heart of our experiment. So we have a very simple glass cell with atomic sources in vapor form inside. And we have this microscope objective pointing from the side. And we have these coils that wound in this pancake geometry to allow good optical access from both down through the objective and also from the side from these angles. That's why we constructed our magnetic field geometry in such a way. Okay, so these molecules that we made, that we were making, starting from the 2 atoms, sodium and cesium, we can now rent the magnetic field and stop it at a different endpoint and see what happened to them. And this is the comparison between if we just starting with one of the 2 different atoms or both atoms present. Okay, so usually we take an image to see what we loaded. We do the following experiment, And then we take another image to see what's at the end of this experimental sequence. So we can post-select our result depending on what we loaded. We see this disappearing of signal of atom first. And on the one hand, here we just still have atoms. And this disappearance of the atoms actually turns out to be these weakly bound molecules once we cross the resonance. We know these are not lost signal because we can reverse our sequence and they recover as atoms. So this process is adiabatic. So sodium cesium atom, people have looked for these kind of resonance for a variety of different alkali combination, and this was actually the first time that was seen for sodium cesium atom, and also using a very different technique, starting with two different atoms, starting with exactly two atoms. Okay, so I want to elaborate one thing. That is to gaining the control over the quantum state. In particular, the quantum state of the molecule by completely mapping the total control of the atom directly onto the molecule. So when we think about making molecule, starting with two particles, the easiest sort of, the most convenient thing to think about is to turn the problem from a two-body problem into a one-body problem. So atom pairs, we think of them in terms of their common center of mass motion as well as the relative motion. Okay, so each one of them is a degrees of freedom that has these letter of harmonic oscillator levels. When we think about molecule, we have similar kind of degrees of freedom. We have the center of mass external degrees of freedom, and these relative degrees of freedom of the two atoms are now actually the rotation degrees of freedom and the vibration degrees of freedom. Okay, so the magneto-associated process map, the center of mass motion from the atom to the molecule and map the internal degrees of freedom, the relative coordinate degrees of freedom, into the internal degrees of freedom of molecules. And in our conversion, the efficiency, how well we can pair up the atoms into a molecule, it depends on how well we can prepare them into the ground state of the motion. And in our case, about sort of jointly 40 to 50%. And it's not fundamentally limited. You just need to do better cooling and better everything during the process. The end result of the molecule, that the internal state is pure, the external state is determined by the initial center of mass motional state population of the atom pair, and therefore 77%. This is what we characterize it to be, or what we calculate it to be, based on the thermometry of the atom. Okay, so from there, we have made the molecule over here, from this molecular potential versus the separation of the atoms. They're still very much looking like an atom, okay? Even though they're weakly bound, they're a molecule, they're very far away from the low vibrational ground state. So that's where we need to connect them with two different color photons, in this case 922 nanometer and 635 nanometer. And we can shine these two photons simultaneously, and these two lasers are are locked to a hyphen S cavity, so then their phase is referenced during the pulse duration. So we can shine these light for on the order of a few microseconds, and we can see now again these oscillation signal, Rabi oscillation signal, that's basically mapping these weakly bound molecules to the low vibrational ground state, and back and so on, go on, and so on, so forth. This is to remind you that this is our sort of you can think of it as a two-level system of the clock that we started out showing you. Basically we can connect this very different energy level, binding energy worth of energy difference between the molecule internal state of one to the other. These molecules, just to sort of going back to say, from here, this is where our 30% number comes from. From exactly 2 atoms, we're able to make molecules with 30% efficiency. The lifetime of these molecules trapped in these optical tweezers is in excess of 3 seconds. Currently, we're limited by sort of two things. One is just the vacuum. This is a single chamber experiment. Has pretty is a single the vacuum is much simplified compared to the conventional quantum gas experiment. These 3 seconds are also limited by the scattering of the light, the scattering of the optical tweezer light. So we saw that if we increase the tweezer intensity, that this time scale decreases. And another thing that it's limited by is simply the cycle time. So we have only 1 molecule that we made. So the statistic is very slow when we only have 1 molecule, and we didn't want to take these measurements for too long because then we had to average for a very, very long time. So this particular plot was taken in the time span of several hours. So you can get the idea how slow everything is. But nevertheless, after sort of 7 years of pursuit, we are able to make a single molecule from exactly 2 atoms. So let me just tell you sort of the most recent things. And this is where I want to motivate a little bit from the perspective of quantum simulator and computers. So we're interested in creating a quantum system for the purpose highlighted here. And we know that there's a variety of physical systems people are pursuing for this direction, and some requirements include that these individual 2-level system, individual quantum system has to be fully controllable, scalable, and capable of applying these entangling operation interactions. Despite such a wide variety of system physical implementation, sort of a main challenge is to really reach in very high fidelity logic operation, high fidelity entanglement in a scalable way. Okay, so of course, what we are interested in is to add to this list. There's many more physical systems not listed down here, but we want to add to this list with molecule in an optical tweezer array. And the reason we think molecule could be a very promising candidates is because the large variety of internal degrees of freedom, which allow us to fulfill sort of a long list of requirements that are sometimes quite competing in one sort of physics package, one physical system. For example, we can think of information storage in the nuclear degrees of freedom, while we allow interaction in the different degrees of freedom, rotation degrees of freedom. So for example, if we had 2 different nuclear spin states, they don't interact with one another. So molecule here doesn't interact with one another very strongly. But if we map one nuclear spin state to an rotation excited state, then these 2 molecules can interact through the dipole-dipole interaction. So if we have an excitation, say here, and another one down here, then after some time, that excitation will exchange through the dipolar interaction. That would be a way that we can leverage to entangle them. Okay, so this is sort of the nice thing about molecule is that if you want sort of 10 different things that you need in one system, you got it, because you have all the states that you can tailor into your application. But the reality is that not only you have the states you want, you have lots of states that you don't want. So this is actually the full picture where I highlighted these 3 states that I want, 0, 1, and the excited state. But then in the background, you can see there's a lot more states nearby. So this is calculated for our molecule, which has a large dipole moment. And a limitation would be exactly those states nearby. So if we want a very fast exchange time, then we have to sacrifice sort of intrinsically the fact that this will be too fast and it will cause off-resonant excitation. Of course, one solution is to slow things down. And if we want some sort of figure of merit of this fidelity threshold of greater than 99.99%, this is theoretical, then we can slow things down to sort of millisecond time scale. We've also evaluated some experimental imperfections, and then we think we should be able to handle then and work toward this direction. Okay. So what we've done is one molecular qubit fully controlled. So we have one molecule in a specific quantum state we want, isolated from everything else. We want to begin to scale up and then begin to see dipolar interaction, begin to leverage that for entanglement. So that's our sort of next goal. So in order to go for that, we start, sort of our next thing is to start with not just one trap of each atomic species, but 10 traps of each atomic species by driving our acoustic optical deflector with 10 different frequencies and focus into our chamber. So here's the image of this 10 sodium atom and 10 cesium atom trap side by side. We can cool all of them simultaneously. So these are these sideband thermometry, where you can see the large asymmetry between the left-hand side and the right-hand side. Left-hand side and the right-hand side. So we can do a good job on the cooling of the atoms. We can cool both species pretty well, so both sodium and cesium. So the control over the atom is actually pretty good. We did face some technical challenges. It turns out there is a lot of optical interferences of these tweezers and nearby sites. So nominally, these tweezers are all slightly different frequency, different by the RF frequencies that we use to drive them. But the tail of these, each tweezer can interfere with the nearby ones, or even, maybe the next one, or so on and so forth. And that RF frequency difference on the order of megahertz can actually drive Zeeman transition of the atom. So we saw that we can, our state preparation is ruined, depends on how close these tweezers are. So in order to do a better job, right now we just eliminate half of the traps, so essentially separate them out more as our current solution. But one can also use spatial light modulator where these frequency, there wouldn't be these interference of frequency problems going on. Okay, so our solution is to eliminate these every other trap, so essentially separate them out even further. We still need to show that we do all the cooling. We still need to show that we can transfer them into molecules. And now it's easy to focus beam down when we only just have one trap, but now with an extent of on the order of 30 micron, we need these Raman beams, the beams that we use to drive the transition, to be as uniform as possible. So what we've done is to have these top half beam shapers, these airy beam shaper. Once we shape our beam and send it through one of these lens, then we're able to get a more uniform top half beam intensity profile to illuminate on top of our tweezer array. With that, recently we're able to show 5 sites, and this is sort of the average of those, where we can see Rabi oscillation for all of them. Okay, so I won't go through any more detail, but our next goal is to begin to actually see dipolar interactions between these individual molecules by first driving rotation transition. Okay, so let me just skip that and jump to the summary. I've shown you that very briefly motivate that the quantum control molecule is very important if we want to do quantum science with these kind of molecule. We demonstrate that from single atoms, we can have the control of neutral molecule at the individual particle level and the individual quantum state control level. And we're now at the point that we're very excited because I started thinking about these kind of applications starting in graduate school, and now we really feel like we're very close to really have the tools to really demonstrate sort of dipole interaction and perhaps even able to entangle them. This is an image of 72 atoms that we're now implementing with our spatial light modulator. So this is much more scalable compared to the acoustic optical deflector, because in that case we have a lot of interference that suffer from our experiment. And we can selectively moving things around to compact. This is an average image, so a single image will be more stochastically filled. And we're also implementing the scheme that's pioneered in the field by Misha Lukin and Antoine Broadway and others, of course, to eliminate the holes and compact up our array. We have other experiments which I didn't tell you about, where we can investigate chemical reaction between these molecules, and these involving molecule transforming from one species into another through these kind of downhill process, and we can completely map out the quantum states of where that energy goes at the end of the reaction. So this is a different experiment that's also carried on in my lab. Okay, so with that, I wanted to acknowledge the postdoc and the students and the collaborator and the people who've gone through the program and really contributed to make this very challenging experiment work. In particular, the most recent results were obtained by Jessie, who's now just defending her thesis, and Louis and Will Cancross, who has moved on to an industry position. I guess if I'm allowed, I wanted to advertise for a postdoc position in the Harvard Quantum Initiative in general. This is application is still ongoing. The review actually hasn't started, so even though it says November. So anyone who's interested to postdoc in my group or other groups at the Harvard Quantum Initiative, you're very much encouraged to apply. Okay, with that, I also want to thank you for your attention.
So I got a little bit confused when you brought up nuclear degrees of freedom. Doing optical pumping is hard even for a single atom. So how can you make sure that you end up in the lowest energy hyperfine state of these molecules?
Yeah, so actually, for the nuclear degrees of freedom, we don't actually need to be the lowest one as long as it's a single one. So we can spectroscopically resolve these nuclear spin states at 850 Gauss. I think these energy spacing is on the order of a megahertz. So in some transition, we're able to see multiple nuclear spin states when we do the Raman transition. We just tune the frequency of the two lasers slightly different. We're able to see them. So we start with a well-defined quantum state of the atoms. We can populate into a single nuclear spin state of the molecule on top of the rotation and vibration state. So we don't do optical pumping. We don't do any more sort of state purification. It's all in the transfer process.
I see. The quantum state is pure to everything except the nuclear spin.
No, it is pure for nuclear spin as well.
So,
it's just that the nuclear spin states are megahertz apart, so we have the resolution to go into one of them.
Okay, so you by doing a post selection?
No, it's just by frequency selectivity. Yeah.
Okay.
So in our case, I believe so. It was certainly more clear in the case of potassium rubidium, which is another molecule we work with, where we can connect 2 or 3 different ones, and you can just change the frequency of the difference of the frequency difference of the frequency difference. Let me just basically just the frequency difference of these 2 lasers a little bit separated by on top of this and another megahertz. In the case of sodium and cesium, I think there's also selection rules in the play. Depends on the intermediate state that we use. Sometimes that also guarantee you to only go to one of them and not multiple nucleus spin state. Yeah, but in general, we can resolve them, and therefore we can choose to only populate one of the states. Yeah.
What's so special about sodium and cesium? Why do you pick those 2 atoms?
Yeah, so sodium and cesium the combination of them has a very large dipole moment, 4.6 dBi, and that is a figure of merit of dipole-dipole interaction. It's going to scale with d squared, and that's the reason we chose them. And then why this specific, why not other molecule in addition to this figure of merit is because these are atoms that we know how to manipulate very well. So these are alkali atoms, and we have a lot of experience. The field has a lot of experience manipulating them. So that's our starting point. We can, in principle, start from any laser coolable elements, and there are, in principle, 25 of them has been laser cooled. But we had to know a lot of information about the molecular spectroscopy and things like that. So sodium and cesium seems like a good bet, and when we started out, yeah. There was
the same question.
Okay. Yeah. So these kinds of experiments are obviously very intricate, right? So I guess I'm wondering about some of the problems that showed up in, for example, the earliest experiments with the Rydberg atoms, where you also have large dipole moments, and it took some time for people to figure out how to prevent those dipoles from coupling to static charges and so on inside vacuum chambers. I presume you have to also be very careful of those kinds of things?
Yeah, so we do, but our dipole moment is much less than the Rydberg atom. So we are less sensitive, but so actually one key thing about our skin, about dipolar interaction, is that we want to work in the absence of electric field. So in the absence of electric field, these are opposite parity states, then this excitation can exchange, and it's not sensitive. These states are all electric B field insensitive. So that's sort of the advantage of the skin. Certainly when we first think about it, when we were first thinking about these type of thing, we were thinking about just mapping whatever works for Rydberg to molecule, but that doesn't really work very well because each of these energy level, if we were to actually turn on the electric field, the stark shift is much larger, megahertz or even larger compared to kilohertz interaction that we will get from the molecule experiment. So we want to work in absence of electric field to have our dipole interaction be the dominant interaction, and then, but on top of that, we're in general less sensitive to electric field compared to the Rydberg atom. Yeah, that's a very good question. But at the same time, we're also slower, so there's different sort of figure of merit. But we hope that we can still have we hope that we still have a lot of coherence. That's and all the degrees of freedoms are intrinsically coherent. These rotation degrees, the excited state is expected to be also sort of seconds kind of time scale. In fact, the limits will be sort of black body radiation, and that limitation will be on the order of a minute. So that's what we think. Ultimately, we hope that we can have coherence time on the order of a minute for these kind of molecules. I think, yeah, I guess the gate time, it depends on if if you're willing to live with a little bit of resonant excitation, so that could be between 50 microseconds to, say, 3 milliseconds.
Thanks for the talk. So I had two questions. Number one, how do you start with a single atom of sodium and cesium? Because it doesn't be very reactive, right? So how do you start with a single atom?
Yeah, so the way that we start with a single atom is just, so this is a technology that was pioneered in the early 2000s. So you start with a laser cool ensemble of atoms. So they're very dilute. They're about million and laser cool in sort of a few millimeter cube space. And then with a tightly focused beam, you can trap a finite number of atoms, and so it could be even number or odd number, and then through the cooling process, there's light-assisted collision that pairwisely ejecting 2 atoms at a time, and you end up with 0 or 1. So then that's how we will get 0 or 1, and then we can take an image to see, okay, we have 1 or 0, and then we know what we started out with, and we can continue with experiments. So once they're trapped in there, we can hold on to them for 10, 20 seconds. Yeah.
I have another question. So how can you explain the stability of NaCs? Because both are alkali metals, so both can give away an electron. So how do you explain the stability of the molecule?
So I think these kind of molecules have a very strong van der Waals interactions. So I think it has the bonding character is part covalent bond and part van der Waals. So it's certainly not as strong as hydrogen molecule, but it still has appreciable binding energy. Yeah, half of EV maybe. Yeah, good question.
Good talk. So I was curious that it's hard enough, to make a system that would be able to create a diatomic molecule, but is there any interest in creating a polyatomic molecule using a similar technique?
Yeah, that's a very good question. So I think the system doesn't really scale very easily, but there is a sort of complementary approach, I would say, and that's using this laser cooling technology. So this is one where it's still this is calcium fluoride, so still diatomic molecule, but people have found ways to laser cool specific class of molecules that they can scatter enough photons to cool it down. And this work is in John Doyle's lab, also at Harvard, and they have shown that they can, they have calcium, which is a metal, attached to fluoride, and that fluoride can be changed to like OH or even CH3. Like they have shown that they can actually laser cool molecules with like 6 atoms. So that strategy is more scalable. So basically, you're able to, in principle, attach anything of calcium and optically cycle on calcium to cool it down to, the larger molecule, they get down to millikelvin. But in the case of calcium fluoride, they're also able to get to sort of few microkelvin temperature. So that system would be much more scalable in terms of the number of atoms that we can do. Yeah.
I have 2 quick questions.
Yeah.
So can you give a flavor for how you plan to do this interaction between molecules and other?
Yeah, so basically, the interaction, so what we're working on in the lab right now is to basically, simplify our diagram to just 2 levels. So this is the ground state that we already populate, and we wanted to go to the rotation excited state, drive the rotation excited state of the molecule. And basically, we had this sort of protocol to prepare, so the 50-50 superposition between the 0 and the first excited state. 2 molecules are here, both are in the 50-50 superposition, but the part where they had these off-diagonal elements, they will exchange, and then we're able to. I mean, this is actually to realize the Bell state, but we don't really need that just to see that the information can or the excitation can exchange. Basically, just sitting side by side, driving into the right state, wait for some amount of time, you'll see dipole interaction exactly, and that's would be on the order of kilohertz. For 1 micron, 1 to 3 kilohertz for 1 micron, we're now obviously farther apart, so it would be more like 100 hertz.
My second question is maybe I'm sort of thinking about this wrong. If you want to do an operation on this array of molecules and then read out the result of this operation, do you have to break apart the molecules?
Yeah. So right now in these kind of way of making molecule, we always rely on going back to the atoms to image and see. Okay, this molecule were in a particular state. But
Again, or does that start?
no, it's just destructive. So, but we are also playing around with ideas where we want to have some other atoms around, and atom can use additional atoms can be a messenger to probe the states of the molecule. So we're developing different kind of scheme to try to use axis atom as a messenger to see the states, or to first just to say whether the molecule that we made was successful, and then hopefully even more sophisticated to be able to detect the state of the molecule. And certainly is a big question and a big bottleneck. In the case of these laser-cooled molecules, they can be optically cycled directly. So there is still destructive in terms of states, but you don't lose the molecule. You just know that you have a molecule in a particular state. Currently, that sort of the limitation to that experiment, the two experiments are actually very complementary. Is that experiment is not as cold, so they're not in the motional ground state because it's harder. One has to do sideband cooling as well for that system. So that has not been demonstrated, but that's something that we're working on as well. Yeah.
In your final slide, you showed the array of trapped atoms. I'm curious, two things with that. One, what is the actual kind of scale of the distance between those?
Yeah, so they're about 3 microns apart.
3 microns. What is the smallest scale that you can do before the interactions start dominating? And is that smallest scale a technological barrier or a physical barrier?
Yeah, the small scale is more technological. So 3 micron is about as close we can get right now. So this has to do with the numerical aperture of the system. It mainly has to do with that and the trapping wavelength that we use, so diffraction limits of these individual spots. So I don't quite remember the sort of specific limitation. Certainly, we will want to get them closer. But we can always say 3 micron is also pretty good because ultimately we might actually want to slow down the gate for higher fidelity. So I don't know. I mean, I think this is a good starting point for us, certainly. Yeah, good question.
Let's thank our speaker again.